You ever look at a weird, curvy shape and wonder, how in the world would you even measure that? I mean, with no straight lines, no perfect angles. For centuries, this was a huge puzzle that stumped even the greatest minds. But today, we're going to crack it wide open. We're talking about a technique so powerful, it can figure out the area of a bizarre, squiggly curve or even the path of a planet. All right, let's dive right in.
I mean, think about it, right? A square. That's easy. Length times width. Done. A circle? Well, it has its own neat little formula. Pi r squared. But then, you get hit with a shape like this. It's got no neat sides, no constant radius. There's just no formula you can pull off the shelf for it. So where do you even start? How on earth do you tackle that?
Well, the very first step is to put on your detective hat. Seriously, before you can measure any shape, you've got to understand it, right? You need to see its unique character. We have to trace its outline, figure out its boundaries. It's all about getting a really clear picture of our suspect here.
And here's the checklist, the interrogation we run to tame this wild equation. First off, is it symmetrical? Because if it is, boom, we might have just cut our work in half. Next, where does it cross the axes? Those are our anchor points, absolutely crucial. Just by asking these simple questions, we take this abstract formula and turn it into a real picture, something we can actually get our hands on.
Okay, so once we have our sketch, our picture of the curve, we get to the really cool part, the creative leap that solves the whole puzzle. And what's amazing is that it's this beautifully elegant idea. It doesn't require some scary, super complex new math. Nope, it's just a brilliant new way of looking at the shape itself.
And this is the best part. The solution, it isn't some ridiculously complicated formula that only a few geniuses understand. It's just a shift in perspective. An idea so simple, yet so profound, it literally changed everything.
So, instead of trying to wrestle with that entire complex curve all at once, we do something way cleverer. We just chop it up. We slice the whole thing into a gazillion, well, technically a nearly infinite number, of super thin vertical rectangles. Each one is so incredibly narrow that it's basically a straight line.
Now, why would we do that? Because all of a sudden the problem becomes dead simple. We all know how to find the area of a rectangle, right? The height of each of these little slivers, well, that's just the height of the curve at that exact point. We call it y. And the width? It's the tiniest possible step you can take along the x-axis, this infinitesimal little change we call dx. So the area of one tiny slice is just its height times its width. Simple.
And now for the final step. It's almost magical. We just add up the area of every single one of those infinite tiny rectangles. We just sum them all up, from where we start to where we end. So here's the big reveal. This whole process, this slicing and summing, it has a name. You've probably heard it before, integration. You know that famous elongated S symbol you see in calculus? That's not just some scary symbol. It's literally a command. It means sum up all the little pieces. Think of it like the ultimate adding machine, one that's designed to handle adding up an infinite number of tiny parts to find the one big grand total.
Okay, so now we have this absolutely incredible tool in our back pocket. And with it, we can start asking even cooler questions. I mean, this slicing method works perfectly when a curve is just sitting there on an axis. But what if the area we're interested in is more complex? What if it's an area that's actually trapped between two different curves?
Yeah, exactly. How do we take our powerful slicing method and adapt it for a situation like this one? We've got a ceiling curve on top and a floor curve on the bottom. It definitely looks a lot harder, but guess what? The logic we just learned holds the key to solving it. Here's how we can think about it. It's really just two separate problems that we already know how to solve. So first, we take our integration tool and we find the entire area under that top curve, all the way down to the x-axis. Then we do the exact same thing for the bottom curve. We calculate the total area underneath it.
And here's the final brilliant move. To get just that area trapped in between, we just subtract. We take that big area from the upper curve and we basically just cut away the area from the lower curve. And what's left behind? It's precisely the little region we wanted to measure all along. It's so simple, so powerful, and honestly, kind of beautiful. All right, so you now have the fundamental method that can measure pretty much any curve you can throw at it. But here's the thing. Once you start looking, you start to see these elegant patterns and shortcuts pop up everywhere. So think of these next couple of insights less as tips and more as, well, the beautiful results that just naturally come out of this way of thinking.
This next one is genuinely one of my favorite facts in all of mathematics. And it was first proven by Archimedes, like over 2,000 years ago. Get this, for any standard parabola, if you draw a rectangle that perfectly contains it, the area under that curve is always exactly 2/3 of the area of the box. Always. It's a fundamental, unchanging rule for every single parabola in the entire universe. How cool is that?
And it gets even better. For a really specific case, finding the area trapped between two standard parabolas, there's an absolutely incredible shortcut. If a and b are just the numbers from the equations that define how wide each parabola is, the area between them is always 16 times a times b, all divided by 3. It's like a real-life cheat code for a problem that pops up all the time in physics and engineering.
So what's the big takeaway from all this? The point is that calculus isn't just a bunch of scary formulas. It's a universal toolkit for solving problems. It teaches us a powerful method. Take any problem that seems impossibly complex, break it down into a ton of simple, manageable little pieces, solve each tiny piece, and then just add them all back up to get the complete answer. It's really a way of taming infinity.
And that leaves us with one last, really fascinating thought to chew on. This whole method of slicing and summing, it works perfectly for a 2D area. But what else can it measure? Could you use the exact same idea to calculate, say, the volume of a 3D object? Or the total distance a rocket travels as it accelerates? What about the probability of something happening in the stock market? The second you realize that it's all just slicing and summing, well, the possibilities are absolutely endless.